For this experiment, we are focusing on vapor-liquid equilibrium or VLE. VLE is very important in chemical engineering because it is used in designing separation processes, especially distillation columns. In real mixtures, the vapor and liquid phases may not behave ideally, so experiments are needed to obtain accurate equilibrium data. At low pressure, the main deviation usually comes from the liquid phase due to strong interactions between components. The objective of this experiment is to produce vapor-liquid equilibrium at atmospheric pressure and measure the equilibrium temperature and composition.
So next, we move to experimental setup and procedure. So for this experiment, this is our experimental setup where this experiment have heater, condenser, vapor temperature, and also another apparatus such as um, measuring cylinder, beaker, refractometer, dropper, glass rod, and conical flask. So for the first step, 5 mixture of methanol and water was prepared in a beaker according to their volume ratio as shown in the table. Second, the refractive index of each mixture was taken and recorded as a liquid phase before heating. Next, valve 1 and valve 2 were opened and the mixture was poured slowly into the heating chamber. When all of the content was already in the heater, valve 1 and valve 2 were closed and the heater was switched on. The fourth one, the boiling point reading was taken and recorded when there was a presence of vapor detected at the output, and valve 1 was opened to collect the vapor product and the refractive index of it was taken and recorded as vapor phase. For step number 6, the valve 2 was opened to collect all of excess product, and step 7, valve 3 at the side of the heating chamber was open to collect the liquid product after heating, and then lastly step 3 to step 7 were repeated for another beaker of mixtures.
So for the result and discussions, we'll start with the distillation column. It is used to separate a liquid mixture based on differences in boiling point. The feed enters in the middle of the column and heat is applied at the bottom, which causes the part of the liquid to vaporize. And the vaporizes up in the column and becomes richer in the more volatile lower boiling point components. At the top, the vapor is cooled and condensed down, and some of this liquid returns as reflux to improve separation, while the rest is collected as the top product. The heavier, higher boiling point components remains at the bottom and are removed as the bottom product. So this graph shows the refractive index of the liquid phase before heating plotted against the mole fraction of methanol. As the methanol mole fraction increases, the refractive index increases until it reaches maximum around 0.4. After this point, the refractive index decreases as the methanol fraction increases further. This graph is used to determine the methanol concentration in both the liquid and vapor phases after heating. Using the calculator mole fractions, the vapor-liquid equilibrium diagram for the methanol-water system was then be plotted. This figure shows the experimental TXY diagram for the methanol-water system. The experimental results were compared with the theoretical data at 77.4 degrees Celsius. The experimental liquid mole fraction of methanol was 0.3279, while the theoretical value was 0.3194. For the vapor phase, the experimental value was 0.5857, which is lower than the theoretical value of 0.6826. These differences indicate deviations from ideal behavior and experimental limitations. There are several factors contributed to the differences between the experimental and theoretical results. The residual heat in the boiler causes overheating, which leads to premature vaporization of the mixture. In addition, condenser fouling reduced condensation efficiency, thus affecting the refractive index readings. Also, vapor leakage from valves and reliance on visual observations of boiling also reduced the measurement accuracy.
In this experiment, we investigate the vapor-liquid equilibrium behavior of a binary methanol-water system at atmospheric pressure. We found that methanol, being the more volatile component, was concentrated in the vapor phase, which aligned with distillation theory. The TSY diagram we constructed followed the expected trend, but we observed some discrepancies compared to the literature values. So these differences were mainly due to experimental limitations such as residual heat in the boiler drum, incomplete condensation from falling in the condenser, vapor leakage through valve, and the subjective nature of boiling point determination.